This is the fourth video from the Year 2 Pure Book, Chapter 5, Radians. In this video, I'm going to show you how to find the area of a sector or a segment of a circle if the angle at the centre is measured in radians. So there is your title, Areas of Sectors and Segments. Before we go any further, I just want to remind you what they both mean. So a sector of a circle is where you've got an arc at the circumference and you join to the centre of the circle. A segment is where you have an arc, but then a chord, which is the straight line, joins the two ends of the arc. So a segment looks like a segment of an orange, which is a good way of remembering the two. A sector has a pointy end, a segment looks like an orange. Now I'm just going to share my screen with you so I can explain this a bit more fully. Because there's a lot of diagrams involved in this and it's much easier if I've got them already made on this PowerPoint. Here we go. So just as a reminder, that then is a sector, it's got the pointy bit. If you're working in degrees to find the area of a sector, it's what proportion we have of the circle, similar to when you're finding an arc length. So that's going to be theta over 360 multiplied by the area of a circle, which is pi r squared. So the area using degrees is theta over 360 times pi r squared. If you're using radians, it's the same principle, theta over 2 pi, because that's a full circle in radians, multiplied by pi r squared. What happens is that the pi disappears, we've got half r squared theta. Okay, because it's theta over 2 pi, that's where the half comes from. Okay, so if you're looking at a segment, so this is the shape of an orange segment, the shaded bit there, it's really just a sector with a triangle cut out of it. So to think about the area, imagine the area of the whole sector, so that's half r squared theta, as we've just seen, and subtract the area of this triangle. Now this triangle is not a right angle triangle, so the formula for the area of that triangle is half r squared sine theta. So there we are, the area is, that's the sector, that's the area of the triangle, and you just subtract the two. If you then factorise that, take a factor of half r squared out, it's half r squared brackets theta minus sine theta. Now, the bit with the area of a sector, you need to learn. The segment, you could try learning it, it's a little harder to learn, or you could just remember that it's a sector, subtract the triangle. But you do need to memorise that A, the area of a sector, equals half r squared theta. Okay, well, let's look at two examples here. This first one here is taken from the textbook. And it's example 11 or 12, I think. Okay, in the diagram, the area of the minor sector. Now the minor sector just means the sector with the small angle, not this big portion, because that is actually a sector as well. That would be called the major sector. So the minor sector area is 28.9 centimetres squared. Given that the angle AOB is 0.8 radians, calculate the value of r. Okay, so let's drill down into that. We already know that the area is half r squared theta. So if we replace the area with 28.9, half r squared theta is 0.8. That gives us that 28.9 is half of 0.8 is 0.4. So it's 0.4 r squared. Therefore, r squared, if we divide by 0.4, is 72.25. Find the square root of that. That gives you that r is equal to 8.5. So that was very easy and straightforward. That was all that it asked. Okay, if it happened to be a long decimal, you would give your answer to 3 significant figures. Here, it's exact. It's 8.5. Next example. A plot of land is in the shape of a sector of a circle of radius 55 metres. The length of fencing that is erected along the edge of the plot to enclose the whole land is 176 metres. So that's this, add the curved arc, add this. Okay, so calculate the area of the plot of land. Well, the arc, we need to find this arc length first of all. It's going to have to be this value here, 176, minus these two values. So that's 176 minus 2 lots of 55. That gives you 66 meters. Now we know the arc. We can then use that to work out the angle, theta, and then from that we can calculate the area. So if 66, the length of the arc, that is L equals r theta, and we know that should be 55 there, shouldn't it? Okay, that gives 1.2 radians for the value of theta. Okay, now the area, using the formula for the area equals half r squared theta, is therefore just going to be found by putting the values straight into the formula. So that should be a 55 there, so make sure if you're taking notes that you put 55 theta rather than 5 theta. Okay, let's look at some examples of segments now. So remember, that's your orange segment. They've missed out one of the examples here and gone straight into the following one. So AOB is the sector of a circle, radius 4 meters. The chord AB, so remember that's a straight line connecting A and B, is 5 meters long. Find the area of the shaded segment, as that's this shaded bit. Well, you can see there we've got a triangle. Again, it's not a right angled triangle. And before we find the area of the shaded segment, we're going to have to know the value of theta. So we've got a triangle with 3 lengths and 1 angle. That could therefore either be using the cosine rule or the sine rule. And to tell which one, well, it's side, angle, side. That should tell you that it's the cosine rule. So we need to use that first of all. Okay, so use the cosine rule to get theta. So in the cosine rule in this triangle, 5 squared, so that's our a squared, is equal to b squared plus c squared minus 2bc cos theta. Putting in the values there, 25 is equal to 32 minus 32 cos theta. That is 4 squared plus 4 squared is 32. Okay. Take the 32 cos theta to this side, take the 25 to that side. That means 32 cos theta is equal to 7. Then, so therefore cos theta is equal to 7 over 32. And theta is equal to the inverse cos of 7 over 32. If you do that on your calculator, don't forget you need to set it up in radians first. So once we've got theta, theta is 1.3502 radians. The area of the shaded segment is half r squared theta minus sine theta, because it's a segment, not a sector. Notice that the value for the angle in radians is not 3 significant figures. It's as accurate as you can make it. If you round it here and then use a rounded value later on in this formula, you get an inaccuracy. So don't round until the very last step. In fact, you would just keep that in your calculator and use it again there. So the area of the shaded segment works out as 3.00, that's 3 significant figures, that's why the 2 zeros are there, meters squared. Now this last example here is a bit more complicated, so I'm going to show you the solution to this one on my board because I think I can explain it better that way. So just hang on a minute while I show you my whiteboard. So here it is, I've written it out again, and this is example 16 in your textbooks, and it's on page 125. If you want to be able to look at it there, you might find it's a slightly clearer diagram than mine. Okay, so it says that the area of the triangle AOC, this triangle here, is 3 times the area of the shaded segment. Now, I don't know if you can see it in my diagram, but the shaded segment is just there. It's slightly hard to see, which was where, if you look in your textbook, you can see it more easily. It's a show that question. In a show that question, you've probably been told this by your teacher many times, you have to put enough detail in each of the steps to make sure it's really explicit what you're showing and where you're going. And I often say that assume that the examiner is yourself 2 or 3 years ago, so you have to explain it really clearly. Okay, so we've got to show this, and with all show that questions, it's better not to start with the bit that you're trying to show, but start with the diagram or the information that you're given. So it says that the shaded segment, the area of that is 3 times the shaded segment. Well, let's find out what the area of the shaded segment actually is in terms of theta, because theta is left in the solution that we're trying to get to. So the area of the segment, we'll use the formula that we've just found. Area of seg, I'll just put, is equal to half r squared theta minus sine theta. I hope you can see that clearly enough. Okay, so that's the area of the segment. Then the area of the triangle, this triangle here, well, that's not a right angle triangle, of course, so we're going to have to use the formula. So area of triangle is equal to half r squared sine theta. Okay, so very similar. So it's not sine theta, is it? It's half r squared, theta is in there. It's going to have to be, if you're thinking in degrees, it would be 180 minus theta. Remember that we're working in radians, so in fact it's going to have to be pi minus theta, because pi is the same as 180 degrees. Okay, so that's the area of the segment, that's the area of the triangle. We're told here that the area of the triangle is 3 times the shaded segment. I know it doesn't look at all like it on that diagram. The diagram's clearly not drawn to scale, but that area is 3 times that area. So this here is 3 times the size of that. Now it would be tempting to therefore put a 3 here and then equate them. But if you think about it, that would mean that the area of the segment equals 3 lots of the triangle. It's the other way around, that the shaded segment needs to be multiplied by 3. So that's what I'm going to have to do. So I'm going to have to do 3 times this, 3 times, I'll put the time sign in, r squared theta minus sine theta is equal to half r squared sine pi minus theta. Now, in order to go very much further, what I really need to do is to have it, because in this there is no sign of pi minus theta, so I need it really in terms of sine theta, not pi minus theta. Now to do that, you need to remember something about sines, and I'm just going to adjust this slightly so I can show you. Now think of the graph of sine theta, and I'm going to do it in radians. There's the graph of sine theta. It starts at 0. That's 0. This would be pi over 2. This would be pi. 3 pi over 2 and 2 pi. And it says sine pi minus theta. So that means sine pi minus theta are angles between there and there. So let's just take a random one, that one there. And if you take it across here, you can see that if this is pi minus theta, well, that is the same size as theta. So in fact, the sine of theta, this angle here, is exactly the same as the sine of pi minus theta. So in our equation here, we can replace sine pi minus theta just with sine theta. Now I'm going to pause that so I can just rub out some of this. Okay, I've removed the graph to give me a bit more space to work. Okay, so in this line I can replace that with sine theta. Let's just neaten this up. So that's going to be 3 over 2 r squared theta minus sine theta is equal to half r squared sine theta, because pi minus theta is the same as theta, gives you the same sign. Now you can see r squared is on both sides, so that just cancels. Half is on both sides, so the 2 at the bottom there cancels with the half. So if I expand this side now, I've got 3 theta minus 3 sine theta is equal to sine theta. Okay, and if I subtract sine theta from both sides, I'm going to end up with 3 theta, realise that you're running out of space here, minus 4 sine theta is equal to 0. And just to make sure you can actually see that, if I tilt it up a bit, there we go. Okay, so that's the end of that. The key bit to that was actually knowing that sine of pi minus theta is the same as sine theta. So you need to watch out for little tricks like that. There's a lot about trigonometry that depends on you really knowing your facts about trig graphs well. So you should be in a position now. To be able to do exercise 5D, which is on page 125 in the book. You probably don't need to do the whole of question 1, which has got lots of parts where you're finding areas, but the rest of the exercise, it gets quite tricky by the end, and so do make sure you really pay attention. As I said, use the facts about the graphs of trig to help you with it, but it's mainly sines that you'll be using. Don't forget to put your calculator into radians. Good luck with the exercise.